Hello, this is the Chapter 11 for Top Hat, where we're going to be talking about alkyne reactions. Okay? So for a lot of these, there's going to be a parallel between what happened with the alkenes and what happened with the alkynes. So lots of times it's just the same reaction occurring twice as you did with the alkene. But there are some quirks with this. Okay? So when we're preparing alkynes, okay, we're going to prepare them in a very similar way we did alkenes, just again, twice. We're just going to perform two E2 reactions. Okay, so here are our leaving groups. They can either be on adjacent carbons, or they can be what are called geminal, which they're on the same carbon. Okay, in the presence of a strong base, as long as you've got a CH bond that allows for the to be able to be ripped away, then you can do the E2 reaction. Okay, and it goes through again two E2s. So you grab base will grab this. This will collapse down, kick away. Now again, you're in the sort of antiplanar, sort of anti-periplanar position right here. Another base can come in, grab this, collapse down, kick away. And so voila, you have yourself your alkyne. Now, for adding HX or just something like chlorine or bromine, iodine, you just do them twice. Okay, so if you're adding Cl2, you're just adding ClCl across there twice. So the first time will go to the alkene, and then you'll go down to the alkane. Okay. When you're adding HCl, so again, you're going to follow Markovnikov's rule. But the thing is, what ends up happening is the halides end up going on the same carbon. Okay. The reason for this is that not only are you following Markovnikov, but you are also, when you get to this point, you're going to attack here. These electrons are going to push up onto this carbon, or excuse me, this chlorine, and leaving the carbocation behind. You can get resonance stabilization with these. This lone pair can come down to make a double bond here. You get nice resonance stabilization. So this positive charge is going to want to stay here, and so the next chlorine can come in. Okay, but notice how the first one is just adding H on one side, Cl on the other, following Markovnikov, right? Because this is primary, that's secondary. You just burn one of the pi bonds. Okay? And then, so this is now an alkene, and it's going to do the same thing. Exact same thing goes with, instead of HCl, you're going to ClCl. But again, we're going to be putting chlorines on either side. Now, you'll sometimes see this. It'll be, it'll say either 1 mole or 1 molar equivalent. Essentially, what they're saying with this is you've got 1 molecule of this, of your alkyne, and 1 molecule of, say, your bromine or your chlorine or whatever. Okay, if that happens, this reaction can only go twice, and it's going to form the this trans structure because it's the more stable of the two. So the okay, but it can't go a second time because you only have 1 equivalent, 1 molar equivalent. So you don't have 1 of this and 1 of that. So you can't do it a second time. So if you see something like this, then it'll do the 1 time. If it doesn't say that, you can assume an excess, so it'll go a second time. Again, if you have peroxides around there, so just like with the HBr, normal HBr with an alkene, right? You switch the preferences, and so if you have one equivalent of HBr in the presence of peroxides, you're going to form this, where the bromine is going to be on the higher ordered side. Now this just means that there's both the cis and trans isomers formed. Okay, so half of it's like this and half of it's flipped over, where the hydrogen is over here and the carbon's over there. You're going to get a mixture. That's all that means. Now, where these come into play for where they start to differ from the alkenes is when you start adding water across here. First time that, so the first addition of the water, so if you're doing oxymercuration, right, again, you've got your carbons here, right, this is secondary, this is primary, you've got oxymercuration, this means that you're going to go on the higher side, higher numbered side, or the OH is going to go higher. And so that's exactly what happens, right? So we've got this carbon and this carbon, right? Secondary versus primary. Okay. The problem is, so if this was stable, we would just simply add another OH over here and H here and go on our way. The problem is this enol here is unstable. So it's an ene for the alkene. This is a double bond, and OL for alcohol. So it's an alcohol directly on an alkene. So like that. So that's not stable. And so what ends up happening is this. So you end up, right? There's two hydrogens here. So the double bond ends up becoming a C double bond to O, and this hydrogen here ends up going down here. So you get what's called a tautomerization. Okay, so but the oxygen stays put. So wherever that first oxygen goes, that tautomerizes into the C double bond O. That rearranges. And this H ends up down on the other side of where that double bond was. Okay, so if you have a terminal alkyne, this is a good way of making a methyl ketone, because you're going to put the double bond here, the other side is going to become a CH3. Now remember with oxymercuration, if there's a here's our two carbons, right? They're both secondary in this case, right? Because this is a CH3 here. So there's no preference, right? So half the time it's going to go here, half the time it's going to go there. And so you get a mixture. You get a mixture of the two. But again, as soon as that first OH goes on, it snaps into the carbonyl, the C double bond O. What is interesting about this is that if we do with hydroboration, right? Remember with this one, the BH3, right? You can tell the hint is that there's peroxide involved, and so it's doing something else, but that's a nice clue that you're going to switch your preferences. So for this one, right, we have a primary and a secondary, and so when you do hydroboration, you're going to end up putting the OH on the lower ordered side. But when you're doing it with a terminal alkyne, it's going to work the exact same way, right? Here's your carbon, right? So CH. Right? So this is secondary, this is primary. We're doing hydroboration here. So we're going to put, right, so here's that H, and we're going to add OH, H, right? So H on one side, OH on the other. Now this is going to flip around, and so now this is the O, and the two H's end up here. But it's the exact same. It works the exact same way as the oxymercuration. Okay, but the preference for where that C double bond O goes is different. It's just the opposite, right? And the nice thing about this is a really nice way of making aldehydes, okay, because it's a really clean way of doing it. Okay. But otherwise, it's exactly the same as what was happening with oxymercuration. So if we're going here, here we go. So if we have this, predict the product, right? So we have a carbon and we have a CH, right? This one is secondary, this one's primary, right? This is hydroboration, so this is OH goes on lower side, lower numbered side. So that means the H is going to go here, the OH is going to go there, right? And so if you were to draw out the intermediate, right, the H is going to go here and the OH is going to go there. Okay. But again, that's not stable. Oops, that didn't work well. So what's going to happen is this is going to tautomerize to this. That. Right. This H here is going to slide over there, and this double bond is going to slide up here. Slide up here to make the C double bond O. But the oxygen stays put. So it was originally on this carbon, it's going to stay on that carbon. That doesn't matter that I did it up and then here it's down. There's free rotation around that. Now, with oxidative cleavage of alkynes, right? So for the alkenes, right, we would have, right, we had our carbon right here, and then we would slice it, and then we would end up putting an oxygen here and an oxygen here. This is exactly the same thing as what we're doing with alkynes as alkenes. However, with an alkene, remember we ended up with a C double bond O because we started with a carbon-carbon double bond, so each side is going to be a carbon-oxygen double bond. With here, the problem is now we need to make, right, we go from a carbon-carbon triple bond. Okay, so now we need, right, now we need carbon 3 CO bonds. Okay, now it's hard to do this. This is just carbon monoxide. You can't really do much with that. However, we can get 3 CO bonds over here. Okay. So for that, so if we make a carboxylic acid, right? So we've got this one, and this one. So we're going to make it on both sides. So if you can, make, so slice this. Right? So if you're here, with the terminal ones, however, you have an extra complication. Okay, so we're going to slice it just like before. Right, we're going to put oxygens on either side on those 2 carbons. The problem is, all we've done is we've sliced it. The problem is this is unstable. In O3 or KMNO4. And so this should actually say CO2 plus water. Okay, so this aldehyde ends up getting oxidized up to the carboxylic acid. That's carbonic acid, which then splits into water and CO2. Okay, just like it does in your Coca-Cola or your beer. Right? It's going to split to make the CO2 bubbles. Now, if we were to come in here and hydrogenate, okay, so this is where we're adding to an H2 across the carbon-carbon pi bond here. Right, so we learned about this one with alkenes, right? So if you've got platinum or palladium on carbon or some sort of metal catalyst, nickel, it's going to convert that double bond into a single bond by adding H2 across here. Same thing happens with a triple bond. You come in here and you add your first one, your first H, hydrogen molecule across here, but this is still reactive, and so it's going to convert this triple bond all the way to the carbon-carbon single bond here. Now, in theory, if you had one molar equivalent, you could stop it here, but that's kind of hard to do with that. And so these end up going the whole way. It can't really stop at the alkene. So what we need to do is, instead of pulling back on the amount of hydrogen, what we do is we poison the catalyst. And so it's active enough to do the convert the triple bond into a double bond, but it's not active enough to convert that double bond into a single bond. So we make it really, really sick. Okay? And there's 2 ways that we can do it. We can either do it what's called a Lindlar catalyst, which is palladium in the presence of quinoline, which is an organic molecule, or palladium and we embed barium sulfate on there. Okay? And remember, this ends up making, remember when you do a hydrogenation, you've got a surface that the hydrogen is getting embedded onto, and then the molecule comes in and goes, attaches it on there. So imagine if you had paint on there and you went and put your hand on, right? All the paint's just going to be on one side of your hand. Okay, same thing here. These hydrogens are going to go on the same side. So that what that ends up meaning is that you end up with a cis double bond. Okay, so if you want to make a cis double bond, you do a hydrogenation in the presence of one of these poisoned catalysts. So either palladium and barium sulfate or a Lindlar catalyst. In both times, you're going to get the cis double bond. Okay. But as chemists, we want to say, well, cis is great. But what if we want to get the trans? Well, we have to, just like when we were adding HBr, when we wanted to switch the preferences, we had to do a different mechanism. And so for this one, what they ended up doing is using sodium metal in the presence of ammonia gas. Okay? So you can usually do and it's what's called a Birch reduction. And so you either, named after Professor Birch, not the type of wood, you either do it sodium in the presence of ammonia or lithium in the presence of ammonia. Okay? And it's this really nice one electron system. It turns very blue. It's very pretty. But the way the mechanism works is this one gives you the trans alkyne. Okay, so this is a nice way of converting a triple bond into the trans double bond. Okay? If you want to see the mechanism is here, it ends up being a one electron system. Right, so the sodium and lithium want to give their electrons away, right, so that they can get the electron configuration, noble gas configuration, and so this gets absorbed by the triple bond, and then things move around, so it ends up being a one electron system, or a mixture of a 1 and 2 electron system. But anyway. So, predict the product. Okay, so for here we've got palladium on carbon. Now carbon doesn't do anything. Okay, so that means this is a full bore conversion of this triple bond into a single bond. And so we're going to get this right here. And so this triple bond is going to get converted directly into a single bond. Okay, because there's no poisoning of the catalyst. Now for this one here we got palladium, but it's got barium sulfate in here. So for here, it's going to be a the poison catalyst, and so you're going to make the cis double bond. Okay, and so for here, right, again you've got this right here. Now remember this, even though I'm showing this as a sawtooth, it's actually straight. It's actually a linear bond. I just usually do it sawtooth just because it's easier to see. And so what we're going to end up getting is this. So see, with the hydrogens coming onto the same side. So you end up with the cis double bond. Opposite is true with the sodium in the presence of ammonia. Okay. So for here we're going to get one hydrogen here and one hydrogen here. Up here we were going to get the hydrogens on the same side. Right here we're going to get them on opposite sides. So we're going to end up with we're going to get the trans. Now, one of the things to remember is that with terminal alkynes, okay, remember this is a very acidic bond when it comes to CH bonds. So you can have a strong base like sodium amide. Okay. Now, one of the things, so sodium amide is this. It is not the same as this, right? So you have to be careful whether we're talking about sodium amide like this, which is used as a very, very, very strong base, or we're using sodium in the presence of ammonia, that does a Birch reduction. Okay, So just be careful. Okay. So for this one, what we're going to do is we're going to use this to snatch. So this negative charge is going to come in here, grab this, kick this away. Same thing here. That negative charge on the ammonia is going to grab this, kick away. Now, on this top one, it could have grabbed this one. That's fine. But it can only do one at a time. It can't grab one off the CH3 because that's an alkane, and that's not particularly acidic. Okay? So you have to be careful. The reason why we're interested in this is because now this becomes a source of nucleophilic carbon. And so we can do a nice SN2 reaction on a primary bromide to make a new carbon-carbon bond. And so this electron here, right, become this new bond here. Okay. Right. These electrons here make a new bond there, and so they make that new carbon-carbon bond there. Okay, so wherever that bromine is, that's where we're going to connect it to the alkyne. Okay. So if we want to design these steps, okay, if we start from here, how do we go about designing these guys, designing this molecule? Well, what we want to do is, one of the first things you might want to do is just draw on those hydrogens, right? Carbons, carbon, CH2, CH2, CH3 here. Okay. So what we're going to want to do is we're either going to want to make that bond there, right? Because it's going to be hanging off of the bond that we're going to make is going to be hanging directly off that triple bond. Okay. So it's either going to be here or here. Now we could technically start with this one, okay? But notice how these three carbons here look a lot like these carbons here. Okay? So let's start with this, right? So carbon, carbon. So let's start with CH3 like this, and then we'll hit it with sodium amide. Okay, the strong base. That's going to grab this, move that away, right? And so what you're going to end up with is CH3, C, right, plus NH3. Now there is a sodium over here too, but it's just taking care of that negative charge. It's not really doing anything. So now we've got a 3-carbon piece. So now what we want to do is we need to make that bond there. So what we're going to do is we need a 3-carbon piece here that has a bromine hanging off of here. And so for that one, it's going to be this one here, right? So there's 3 carbons here. Right? So all we need to do is just dump in this 3-carbon piece here, right? And so that's going to grab there, that there. So this is a nice SN2 reaction. And so what we're going to get is CH3, C, triple bond C, and then carbon, 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 right? And this is that new bond there. Okay, so carbon, 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 right? Here's this side, and then on the green, it's right there. So these are the 2 bonds we can do. So that's how we go about putting together a carbon skeleton using an alkyne. Now, we can go a step further and say, hey, what if we want to put in a functional group? Okay, so what if we want to come in here and we want to design this molecule? We know we're going to probably have some sort of alkyl halide, and we need to start with acetylene here. Okay. And so one of the things we're going to want to do is we're going to say, okay, we know we have to go here. We have to go through this triple bond. We can get to this in a minute. But what it might actually be helpful to do is to start here and say, how do we put in how do we make a primary alcohol? Okay. So if we start here, what do we have to do to make this final product? Well, we know that we can make a primary alcohol if we start with a terminal alkene and do a hydroboration reaction, right? So remember, right? This is going to want to go, right? So this is secondary, that's primary, and so you're going to want to go, so it's going to go HOH, right? When we add it to it. Now, if we want to have this, to do this on our molecule, which would be down here, the molecule better look like this, okay, with an alkene here, so that we can do that hydroboration to put it here, right? So we can have H on this side, OH on this side, and so we can do here. Now the question becomes, how the heck do we make this alkene here? And you're like, wait, hold on, where did we get this one? Well, we're just saying we don't know yet. We're just saying in order for us to do this reaction, the molecule better look like this. Okay? We'll get to building this in a second, but we just need to know, we need to get the functional groups in the correct place in order for us to do this. Now the question becomes, how do we get a double bond in here? Well, remember, we are trying to start with a double bond, or excuse me, with a triple bond. So there's an easy way of doing this. We can just convert the triple bond into a double bond like this. It's you know, we just learned about this. We can do this. There's other ways that we can make a double bond, but since we know we're going to have to start with a triple bond, why don't we start it there? And the easiest place to have that triple bond is right there, because then all we have to do is either H2 or Lindlar, or actually you can do a Birch reduction for this, okay, depending on which one, because there's no sister trans right here. So you just need to convert that triple bond into double bond. Aha! So now what we're seeing is, here's our acetylene, right? Here is our alkyne piece. So that means that this part here must be the part that we have to add on to it. So here's the other piece, and we need to make that carbon-carbon bond here. So what we've done is we've actually dealt with the second half of the synthesis first. How do we get that? How do we get the functional group in the correct position? And so once we do that, then we can figure out how the heck do we get the the carbons in the correct positions. Okay. And since we know we have to go through a triple bond, that helps. So how are we going to do this? Well, we're going to take our acetylene anion here, and we're going to do a nice SN2 reaction. Right? So we do this SN2, and then this is going to get kicked away, and so we're going to form this new bond here. So these electrons are going to form that new bond here, and so here are So here are the here are the electrons on this side. Right? Well, how are we going to form this? Well, that's pretty easy. Right? We're going to take acetylene and hit it with sodium amide, and that's going to rip this away, and so we have what we need. And so here's how we think about this. This is what's called retrosynthetic analysis. How do we make this? Well, we start with this and put it to hydroboration. Well, how do we make this? Well, we can start with this and do a Birch reduction, or use a Lindlar hydrogenation, right, to get here. Well, how do we make this? Well, we can take this acetylene anion and mix it with this alkyl bromide, okay, and that when we mix these two together, we can make this. Well, this we can get off the shelf, but what about this? Well, here we have to take acetylene and put it onto, add it with sodium amide. So this is how you kind of want to think about the synthesis, but the actual synthesis itself would start from the acetylene here, add this, make this part, reduce that down to the double bond, and then do hydroboration. The general rule of thumb is that the first half of your synthesis is just getting the carbon bits in the correct orientation. Okay, get your carbon skeleton where it needs to be. Then you can start dealing with the actual putting into the functional group. Now, but this part here is the one you want to focus on first, so that you know what to do here. You know what you have to aim for to get here. Okay. So if you want to look at this, say, okay, here's the carbon bits we can use, and we can use anything we need. So, we have a primary bromide. Okay. So how do we know how to do that? Well, we know that we can do, right, if we have a double bond, right? If we add HBr in the presence of peroxides, right, then that means that the H is going to go on this side and the Br is going to go on the other side. Okay, so you're going to end up with this. Right? You're going to end up with your primary bromide. So what that means is that our last step is going to be HBr with presence of peroxides, and our molecule has to look like this, right? So that we have, right, secondary versus primary. So how do we make this? Well, just like with the last one, right? If we have a double bond here, if we have these triple bonds, the easiest way to make this one is to just start with the triple bond, okay? And to come in here and you say, okay, well, come in here and say, okay, well, I want to do H2 Lindlar. And that will convert this triple bond into a double bond so that I can get the HBr and peroxide to add the bromine in the correct orientation. So how are we going to do this? Well, the easiest way to do that is to break it up into two parts. The acetylene part here, and then this 2-carbon piece here. And since we have a hydrogen hanging off on this side, we're going to want to have a hydrogen hanging off of the other side here. And so what we're going to need is we're going to need here, and then we're going to want to dump in a 4-carbon piece here with the bromide. Right, we're going to need this 4-carbon piece here, and then we're going to need this piece here. So here are our 4 carbons here. Here's our acetylene, right? And this is where this is going to attack here, kick this away, and so this is where the new bond is going to be. So how do we make this? Well, we can come in here with the presence of sodium, sodium amide. Now you could have taken off this one, that's fine, as long as you only take off one. And that's our synthesis. Now this is incredibly powerful, okay? And so this is cyclopiamine, okay? It's an alkaloid from this penicillium, and it's a potential antibiotic. So when you're doing natural products, you isolate compounds actually from a lot of plant material, and at NCCU we have a professor that does that. And so these can have interesting medicinal properties. But the problem is, if you isolate something, it shows, oh hey, this attacks cancer. Well, how do you know it's that particular molecule and not some very small 1% contaminant that's in there that's super potent? So what you do is you end up actually synthesizing the molecule from scratch and then testing it and see if it has the same properties to it, because you're not likely to have that same contaminant if you synthesize it from scratch. And so you can have these these molecules like this. This is very complicated, and so you can come in here and you can think about for here you can being able to put in this bond here, and these various bonds, moving these around, and so you can end up going here and you end up with D-proline, which is the unnatural form of or the non-normal form of it. The normal one is usually the L-proline, stuff right here. But you can actually see this ring here, right there. But you can start with a very inexpensive chiral piece and start building it up. Okay, so but in order to do that, you have to go backwards to figure out, okay, how do I make this? Well, I can do this. Well, how am I going to add this? How can I make this? Well, I can add this part onto it if I have this part here. Well, how do I make this? Well, I can do, these two pieces, put this together. So this part here is this part there. Well, how do I make this? Well, I can start with this to make that. Okay, and usually you start with hundreds of grams or a kilo of this material, and you do this chemical steps, and for a lot of these things they're not particularly efficient. And so if you do this one here, then you end up maybe with milligram quantities of this, but that's fine. That's enough for you to test. Okay? Now, cyclopamine is is kind of an interesting molecule because the reason for that is the cyclop. You know, Cyclops from the Odyssey, right? It's got the one eye. So it turns out that if pregnant cows are ingest this cyclopamine, what's going to happen is they end up getting a birth defect where the halves of their brains don't split properly during fetal development, and so what ends up happening is they end up having one eye in the middle of their forehead, and so they look like a cyclops. So it's pretty interesting. Now the calf that usually doesn't. There's lots of other things that are wrong with the calf, and so they don't generally live very long. But this is the source of the birth defects. So, yeah, good luck.